Hello and welcome back to the 7th part of week 1. This is going to be our final discussion in the context of greedy algorithms. And in this video, I want to demonstrate that the algorithm that we came up with last time is actually a valid approach for finding a stable matching. Let me quickly recap what our algorithm was doing. We had the men propose to their current best options, and we had the woman accept their best offer, even if it meant breaking off a few engagements here and there. We kept building up the list of engagements, and we stopped when nobody was single at the end, and that's when the engagements solidified into a matching. So we want to talk about 3 aspects of this algorithm. The first is termination. We want to make sure that the algorithm actually terminates on all instances. The second is the nature of the output. I want to say that the engagements that we have at the end actually correspond to a perfect one-to-one matching. By perfect, I just mean that everybody is matched, nobody is left single. And by matching, I just mean that every man is matched to exactly one woman and every woman is matched to exactly one man. So that's something that we want to show. And finally, we want to argue that this matching is stable. So that was our goal, to avoid blocking pairs altogether. So those are the 3 things that we are going to try and establish in this video. Before we dive into the proofs though, let me make a quick historical remark here. This is a really famous algorithm which was published in the 60s by a pair of mathematical economists, David Gale and Gale Shapley. And the algorithm is widely credited to them. In fact, if you look up the algorithm, it often goes by the name of the Gale Shapley algorithm or the GS algorithm for short. In some places, you will see it being called the Deferred Acceptance algorithm. That's a more descriptive name referring to the nature of what the algorithm is doing. And it turns out that this algorithm actually came up in the context of the college admissions problem back in the 60s. And in fact, it even turns out that a very similar algorithm was actually already being used in practice in the National Residence Matching Program in the United States. And this was in use almost 10 odd years before the algorithm was formally published and its theoretical properties ascertained. So this is just to say that this whole idea that we discussed last time must have felt like a reasonably natural approach to actually matching agents with each other, and in a way that kept them happy. I'm not sure if when it was being used in practice, if the practitioners were aware of all the nice properties that this procedure had, but the fact remains that it was one of those algorithms that was adopted even before it was published. So that's, I think, an interesting historical anecdote about this algorithm. And now let's go on and actually demonstrate that it does have these nice properties that we are advertising. First, let's talk about termination. We briefly alluded to this last time also. So let's think about what's happening from the perspective of the men. And if it's helpful, you can think of this algorithm as being broken up into one proposal at a time, instead of thinking of it in terms of rounds, which is how I described it last time. So the way the algorithm works now is that as long as there are single men in the pool, you choose one single man and have him propose to his current best option. Okay? And we keep doing this as long as they're single men. So what's happening from the perspective of the men is that we imagine keeping a pointer at their current best option, pointing to their current best option. So to begin with, for all the men, the pointers will be pointing to the top ranked woman on their list because that's where they are at. But as they make proposals, these pointers will move further down. And notice that the pointers only go further along in the list, they never come back. And the reason for that is simply that by design, men never propose to women who have already rejected them. Whether it's women who reject them immediately or reject them after being involved in an engagement, it doesn't matter. Men never propose to women who have already rejected them. Therefore, the proposals are always made in decreasing order of rank, and you never propose to the same woman twice. As a result, the total number of proposals that are made in any run of the algorithm is going to be at most n squared. Now, you might say, what if there are still single men after all the proposals have been made? Because remember, our algorithm is basically a while loop based on the existence of single men. So the outer loop looks like this. While there exists a single man, we are going to have one of the single men make a proposal to the best option that they currently have. But what if there is a single man, but he's completely out of options, right? In this case, what does the algorithm do? Isn't it going to get stuck? Well, let's think about whether this situation can actually materialize. Let's think about what we are saying here. We are saying that there is a single man, but he has no options, which means that this gentleman must have actually proposed to all the women on his list, and he must have been rejected by all of them, because that's why he's still single. And let's think about if this is even feasible, because if at some point there is a single man, then there is also at least one single woman, because it's not possible for all the women to be matched while there is a single man, right? There are n men and n women. So for all the n women to be matched, they actually need n distinct partners to be matched with. But we know by assumption that there's at least one man who's not matched with anybody. Therefore, there must be a woman who is also not matched with anybody. So let's call that woman W, and let's call our friend here, the single man, M. Now, remember we said that we are in this situation because M has been rejected by every single woman that he proposed to, and he has proposed to all of them. So what happened when M proposed to W? Well, it's either one of two possibilities. Either W rejected M immediately, or W accepted the proposal but rejected M later. Either way, M was rejected by W because M did go further down his preference list, and in fact we are in this situation where M has actually been rejected by everyone. So in particular, M was rejected by W, either immediately or after some time. But now let's think about W. A woman in general is going to reject a man only if she already has a better option, right? So either at the time when M proposed to W, W was engaged to somebody that she liked better than M, or if she actually accepted the proposal and rejected him later, it must have been in favor of a new proposal that was superior to M, right? But this contradicts our assumption that W is currently single. Notice that a woman, once engaged, never goes back to being single. If she breaks off an engagement, it's only because she has a better option, right? So that's the contradiction. We cannot be in a situation where a man has been rejected by everyone and is single at the end, because that would imply the existence of a single woman as well. And then when you think about the interaction between the single man and the single woman, as M was making his journey through getting rejected by everyone, you realize that there's going to be a contradiction, which is what we just discussed. I do hope that this is clear. In case it's not, feel free to take a pause here and convince yourself that this checks out. Okay, so we do know that in any run of this algorithm, at most n squared proposals can be made. And once we have run out of proposals to be made, we actually have no reason to continue. Everyone is guaranteed to be engaged with somebody. Of course, the algorithm may terminate faster than n squared. You might be in a lucky situation. For example, if all the women who are ranked first by the n men happen to be distinct, then the algorithm is going to wrap up with just n proposals. Now, here's a fun puzzle. Can you come up with an instance of this problem where the algorithm is really compelled to make lots and lots of proposals, right? I gave you an example where it wraps up with just n, but can you force it to make many more? How many can you actually push it to? Think about that and Let's continue our arguments in the meantime. So we have argued for termination. The next thing that I want to talk about is the fact that the output is a matching. We've already seen that no man is single at the end, so every man is engaged to somebody. But also note that the nature of our engagements is such that no man is ever matched to more than one woman at any stage of the algorithm, right? So you're either single or you're matched to somebody, but you're never matched to more than one person at any point of time. So what we are maintaining as we go along is certain near matching. The fact that nobody is single at the end is really the crucial factor here. Other than that, the fact that a man is not matched to two women or no woman is matched to two men is simply by design, by the fact that the engagements that we maintain as we go along are themselves one-to-one. So we never encounter this sort of a situation. So take a minute here if you need to convince yourself that the output is actually a one-to-one perfect matching. Everybody is matched when the algorithm is done. Now, the last thing that we need to establish is that this matching is in fact stable. There are no blocking pairs. And to show this, let's proceed by contradiction. Suppose that the matching that is output by this algorithm does have a blocking pair. And let's say that blocking pair is between M1 and W7. That's just a random example here. What does this mean? Let's say hypothetically that in the output of the algorithm, M1 is matched to W3 and W7 is matched with W5. For M1 W7 to form a blocking pair, it must be that M1 prefers W7 over W3 and W7 prefers M1 over M5. Okay, that's just the very definition of a blocking pair. So this must be the case. So now let's think about what the algorithm must have done. In the algorithm, M1 must have proposed to W7 before he proposed to W3. And we also know that M1 did propose to W3 because that's whom he's matched with at the end, which means that at some point W7 must have rejected M1, right? So when M1 proposed to W7, he may have been accepted at that point, but he must have eventually been rejected, because if at no point of time W7 rejected M1, then W7 and M1 would be matched at the end of the algorithm. So W7 clearly either moved on or already had a better partner to begin with, right? That's why M1 was compelled to move further down in its rank list and end up with W3. Now, from W7's perspective, why would she do this? Why would she reject M1? As we have seen, the only time that a woman rejects a man is if she has a better offer, right? So if at any point W7 did have a proposal from M1, and we know that she did, her final matched partner can only either be M1 or somebody better than M1, right? Because in particular, even if she was engaged when M1 proposed to her, if she was engaged to someone that she liked less than M1, then she would have broken off that engagement in favor of M1. And further down as well, the only reason that M1 was eventually rejected by W7 is because she got a better offer. So it must be that W7 actually prefers M5 more than M1. So the fact that by proposing a blocking pair, we are saying that W7 prefers M1 over M5, that's simply a contradiction. It contradicts the behavior of the algorithm. It's not possible that both of them prefer each other over their matched partners because of just the nature of how the algorithm works, the mechanics of the algorithm. And if you remember when we were discussing what should we do in this algorithm when a woman gets a better offer, and we said, well, if she gets a better offer, she must greedily accept that offer and break off the engagement that she might currently have. And this was exactly the motivation to do it that way, so that this proof here goes through and we can be rest assured that there are no blocking pairs whatsoever. Once again, if that was a lot to take in, feel free to take your time and rewind this argument, or better yet, try and see if you can come up with it once again on your own. And we will have some fun problems in the assignments that will hopefully let you practice your notions around the stable matching problem. So that's it for now as far as greedy algorithms are concerned. In the next week, we will be talking about something called matroids, which is an abstract combinatorial construct. It's a very interesting combinatorial object which happens to capture a very key structural property that makes a greedy idea actually work. So it's a very cool result that we're going to see next time. We're going to set up a fairly generic optimization problem and see that this optimization problem admits a greedy algorithm if it has the so-called matroid structure. And once we have this result down, we will be able to come up with valid greedy algorithms for other problems simply by showing that they have the matroid structure, as opposed to trying to prove the correctness of greedy by hand from scratch, which is what we have been doing this week. All right, so with all that said, I think I had a great time. I hope you enjoyed this as much as I did. And I'll see you in either the live sessions or just back next week. I hope you have a great time solving the practice assignments and the graded assignments and all the food for thought questions that come your way as a part of the week 1 coursework. Do get in touch if you have any questions at all. I'll certainly look forward to hearing from you, and see you next week. Bye for now.